Let's see. Logitech. Okay. All right. So now let me get as much of the board as possible. And recording. Okay. So we're going to review Chapter 16, Solubility and Complex Ions.
Can I jump right in with a question?
Question, yes.
Okay. So, solubility is an equilibrium position, it says.
Yes.
And so it is a number that is expressed in molarity, molar.
The way we're going to use it, yes.
So
it doesn't necessarily have those units.
Okay. So it's used, for example, in question number 1 on the review.
Mm-hmm.
We have lead iodide.
Yes.
And we have its molar solubility as 1.52 times 10 to the negative 3 molar. I guess what my brain wants to know, well, how is that number used? I can see the formula, but my brain just needs an explanation. Where did that number come from, and why is it used to calculate the equilibrium or the solubility product in this case? Because it's a solid, that's why it's solubility product, right? Okay.
We're going to go this way, and it's going to make lead 2+ ions and iodide and 2 iodide.
Now, why do we say we're assuming that we're putting the solid in water to get the aqueous, to get the ions to, or whatever, separate the charged particles to.
Right, we're going to stick with aqueous solutions.
So where did that number come from, the 1.52? Like,
that was given to you.
I know that.
Oh, you can, yes.
How was it calculated? How did that get derived?
It can be measured. Yes, all you have to do is put this in solution, allow enough time for equilibrium, and then measure one of these.
Okay, so it was
right.
That's what I wanted to know, is like, how did we get that number? Okay, so and then you use the formula to just define the coefficients in order to have our exponents for the next calculation.
Yes.
I get all that.
Right, KSPs.
I need sometimes a little more background explanation for my brain to be like, okay, this is why we need this.
Like that. So that'd be the KSP.
And that's so that we can find the concentration of.
Well, we know the concentration of this one. Since the coefficient is 1 here and 1 here, then if this says how much of that goes into solution.
Yeah.
Right? If so much of this goes into solution, then it will produce one of these and 2 of those.
Okay.
So the concentration of that one will be 3.04 times 10 to the minus 3. This one will be that concentration, and this one will be
oh no, wait a second. So you have to use the coefficient in the calculation and square it as well.
right. This is the KSP expression, but you have to know what these values are. This value is the same as that because it's 1 to 1.
Okay, so I guess I just thought that the coefficient was covered by that exponent factor there.
Mm-mm.
No, it's
No.
not. Okay.
No, you have to determine what this is, and it would be twice what that is.
Okay.
Okay, so then you just plug in the numbers. Square that one. I must square it. Here it is. Times. So if I calculate it correctly, that's 10 minus 8. Yeah, that's probably the trickiest part. That's why you need a balanced equation. And if you're starting with solubility, what relation? The solubility refers to this term. How much of that goes into solution?
Mm-hmm.
And then the relationship, the coefficient relationships tell you what these concentrations are.
So oh my gosh, where's barium? I obviously didn't memorize this chart. I cannot find barium.
Barium?
Yes.
It's alkaline earth. Oh, you're looking at the solubility chart.
No,
right?
I'm looking at the
That's periodic table.
Mm-hmm. Oh, okay. Shh, don't tell the teacher. Can you do number 6?
Number 6, okay. All right. The iodate equilibrium concentration in a saturated solution of cerium iodate is certain value. Calculate the KSP. Okay, so we're going to have this compound. In equilibrium with cerium. Right? Since that's -1, this one has to be 3+. And then 3 of these. All right, the iodate concentration. This concentration is given, so you don't have to multiply it by 3. Okay.
So,
but in order to do the KSP, you need this expression. And if this is that value, then this is going to be 1/3 of it. Right? Because for every one of these, you get 3 of those, and this is 3 of those. Is that what threw you?
yeah.
Okay.
Yes, so.
Right, so this one is going to be 1/3 of that value. Divided by 3.
That's cerium?
Cerium.
Oh, it's down in the, whatchamacallit. Down there at the bottom. I just couldn't find it on the chart.
I can't either.
It's at the
I
bottom.
don't use it that much. Here it is.
Yeah.
Lanthanides. There you go. Okay. So once you get past this thing right here, you're probably okay.
So when we read that sentence, the iodate ion in a saturated solution of cerium iodate.
Yes.
So when we see that word saturated, we're assuming that it's put into a water again? Like, I just want to make sure I understand the
Yes.
language. And the way it's,
Whenever we're talking about solubility, every solid that's in equilibrium with its ions in solution is saturated by definition.
so, cerium is,
Okay.
is iodate in our chart here? It's just a -1. Cerium.
Okay, I get 4.12 times 10 minus 10. Did I do it right? It agrees with the worksheet. And the answer key. And of course, this is like any equilibrium. We never put the units in. Because it just gets way too complicated with all these powers.
So that kind of be the same thing for number 11 then?
11, solubility of silver phosphate. Terminal concentration of silver ion in a saturated solution. Okay, yeah, it would be similar. It's just we wouldn't go all the way to KSP. For the benefit of our viewing audience, we'll do the whole thing.
Sorry, you skip to number 11.
Yes, Ag3PO4.
Silver phosphate.
Uh-huh. Oops. That. So we have 3 silvers and 1 phosphate. And we're given solubility, 1.55 10 to the minus 5. Solubility. So that means this many moles per liter of that compound goes into solution, which means this concentration is going to be 3 times that. So all you really have to do is just say 3 times. Molar equals concentration of silver. I'm pretty sure. Yes. The way I set it up in the answer sheet was I just turned these coefficients into a conversion factor and used them on.
So, Number 15.
Number 15. Okay. Let's see, KSP of lead 2 sulfate is 1.3 times 10 minus 4. Calculate solubility. Okay, so we're going back the other direction. Except this is in a certain concentration of sodium sulfate. Okay. So here's lead sulfate going into solution. Lead 2 sulfate, I should say. Okay. And the KSP, just put it over here so I can put my paper down. It's 1.3 times 10 to the minus 8. And the solution, and we want to know solubility in 0.0037 molar sodium sulfate. Okay, the first question you ask yourself is there a common ion? Is there something in this solution that will affect that equilibrium? And it will, because you're starting out with a sum of this. So the question is, what's the solubility? And in order to do that, we need to ask ourselves, what's the relationship? So it's 1 to 1 to 1, right? So if we pick this one as our unknown, then it will give us the solubility. So we go to ice. Actually, we don't need that, so I'll put ice over here. So what's the initial concentration? Well, we're starting out here with 0, right, before equilibrium. And we're starting here with 0.037 molar. Okay, so what change are we going to get? Well, since we've got none of that, it's got to go this direction. It just won't go as far as it would if that were 0 too. So this is going to be x, which will give us the value of that. We're going to add some of this since it's also 1 to 1. This is x plus 0.0037. Now you can write, now you can set this up as your terms in the solubility product. So that's going to be KSP equals 1.3 times 10 to the minus 8, which is equal to sulfate, and then that's equal to x times x plus 0.0037. Okay, so this is going to be x times that is x squared. Actually, okay. I don't think we can get rid of x because x is going to be very small to begin with, right? And there's no guarantee that it's going to be sufficiently less than this that we can throw it out. So let's say x squared plus 0.0037 x is equal to this number here. And Well, I might as well do the whole field. Let's see, how much room do I have? I got some room left over here. All right, so this is going to be, to use our quadratic, we have to do that, x squared plus 0.0037 minus 1.3 times 10 to the minus 8. That means that x is going to be, let's see, we'll just write it up here, plus or minus square root of b squared minus 4ac all over 2a.
So the a value is always the number in front of the square.
Yes,
X.
and this is the b, and that's the c. So we're minus b, 0.0037 plus or minus square root of 0.0037 squared minus 4 times a, which is 1, and c, which is minus 1.3 times 10 to the minus 8, all over 2a, which is 1. So if we resolve that whole thing, x could be either 3.51 times 10 to the minus 6 or minus 3.70 times 10 to the minus 3. And the minus says that's not a valid number. Now I'm curious, what if we did say that this was small, and then it'd be x times that is equal to this? So it'd be this one divided by, no, square root of. If we throw that, no, if we throw this x out, it would be x times that. 0.0037. Did that wrong. Try it again. 0.0037. Okay, we could have get the same value. If we just say this one is significantly smaller than that one, then that one goes out, and it's this times that, which means x equals this divided by that. So you get the same number. The whole thing is, if you do it this way, you don't have to check. If you do it the other way, you've got to do your 5% rule and be sure it's right. Whichever one you want to do. See what happens. I do. Check it. I have my quadratic equation on the back of my calculator. So that was a little bit more involved.
Can we discuss number 13?
13. Okay.
I mean, I'm just looking at it.
Oh, okay.
So I mean, we're just picking the lowest number there, right? the lowest solubility would just be the lowest number, the lowest.
Yes, the key here is to pick your X's, to pick your X correctly. Make
I
it,
mean,
yeah, go ahead.
why do you have to calculate anything? Can't you just look at those numbers and, that's what I'm asking. Wouldn't you just pick the lowest number, which would be 1 times 10 to the negative 72?
No.
No? Yes, not.
No, the reason for that is you're talking about the KSBs and the solubilities are different calculations. If you're comparing solubilities, you can't compare the KSPs directly unless their solubility products are similar in the way they're calculated.
Okay, so we do have to do math on these.
Yes.
Okay, so they gave, okay, I see. That's the solubility product values, not
Yes.
the solubility.
Right.
Gotcha. Okay, I get it now. No problem.
If we were to compare C and D only, we could compare the KSPs directly because manganese sulfate breaks up into 1 manganese ion, 1 sulfate ion. Mercury sulfide, I said sulfate, manganese sulfide, and mercury sulfide also breaks up into only 2 ions. In that case, you can compare the KSPs directly.
And in that case, the mercury sulfide is smaller.
Let's see. Mercury is minus 54. Yes. Yes, so in that case, D would be
Right.
the least soluble.
Right. No, I see now. Okay. It's getting that
The difference between,
solubility and solubility product.
right.
KSP and
Yeah, one's an equilibrium calculation and one's a position.
I can just keep asking like that. I'm happy to hear explanations on all kinds of stuff.
Yeah, perfect example is 12. With 12, you can compare each one of those solubility products.
Because they break up 1 to 1.
Right, because they're all the same stoichiometry.
So which one is the most soluble? Let's see, that would be lead sulfate.
True.
Hmm?
That's true. Lead 2 sulfate. And then in the old parlance, that would be plumbous sulfate. Okay, let's see.
Where's Jimmy?
Yeah, that's a good question.
He's missing.
And he's not signed in, so he's either working or asleep. Maybe they had him doing double shift.
Let's see. Just for the sake of I don't know, like questions like number 19 and 24, like just talking about those helps me like just to understand more about
Okay.
things that are happening.
Okay, so 19. We're talking about the dissolution of zinc sulfide.
But boy, I do not remember what amphoteric means.
Oh, okay.
Just right off the bat, I'm looking through the answer. I'm like, I don't even remember what that means at the moment.
I'm not so sure that that's even a valid expression. Amphoteric means that it can go one way or the other. And we've only used that in terms of acid-base and the water molecule. Water can either be an acid or a base.
Okay.
So I guess what they're saying here is zinc could act as an acid or zinc could act as a base. But that doesn't explain it. So if zinc were going to act, let's just take them one at a time. If this ion were going to act as, well, and this in hydrochloric acid. Yeah. So wait, before we do anything else, this breaks up into these ions, right? So, are they going to have any effect on this reaction? Well, let's see. How about the chloride? Zinc chloride is completely soluble, so chloride won't have any influence. Right? But the hydrogen ion will interact with the sulfide, and it will produce, let's see,
Where did you get to? Just
Because of that.
Pulled out of solution? Pulled out of the, because it's in a dilute. So you're assuming.
This one right here?
Yeah.
No, that's stoichiometry. That has nothing to do with this. I mean, it has nothing to do with the number here of one there and one there.
Okay.
It has to do with this stoichiometry. So it's determined from here, H2S. And if we look at H2S, our solubility table, well, where is it? Nothing there. Okay. Well, let's look at solubility of H2S. Is it in? Okay. All right, let's look at our okay, if we look at page 17 in this color chart, what happens when you add H2S to a solution?
Wait, where's 17? Oh.
This one, pretty color.
Got it.
This is the only reference I have to H2S. It solubilizes 3, 4, and 5. So, what is the equilibrium position for this right here? That's the question.
Wait, it says here that zinc sulfide is insoluble. Is that?
Right. That's because the
But when it's mixed with the hydrochloric acid, then it will break up.
right. What we're doing is we've got an equilibrium set up here, forming H2S, and what it's doing is it's a coupled reaction. So it's taking this part here and reacting it with that part to make this. So it drives the reaction that direction as it pulls this out of solution and makes H2S. Now H2S could be soluble. In fact, it is. I'm sure this is soluble. But so are these. And this is an equilibrium situation between these ions and that soluble compound. So in the process, it takes this and it draws it it puts more of this in solution as you draw this out of solution. Okay. Does that make any sense?
Okay, say that again. It puts more zinc in solution?
Right. If you just look at this in water, okay, you've got an equilibrium here. Now you introduce sulfide ions.
No, you mean hydrochloric
I
acid.
mean, hydrochloric acid, excuse me. You introduce the hydrogen ions. And the hydrogen ions combine with these sulfides to produce H2S. It drives their equilibrium that direction, which, coupled to this one, drives the equilibrium that direction. As it pulls these out, then it makes more of this go into solution.
Okay, so
Oh, so the answer for 19, all right, let's see which one fits. Zinc is apateric is just a confusion. The sulfide ion concentration is decreased by the formation of H2S.
that would be what we just said, right?
Yes.
Okay.
That's exactly right.
The sulfide ion concentration is decreased because it's turning into,
H2S.
would you say hydrogen sulfide? What would you say?
Yes, hydrogen sulfide. Mhm.
Never mind, I'm not sure what my question is. Just long.
I hope it wasn't about 19. Because I just erased
No,
it.
that's okay. It's more like when I look at these problems, like, how do I know that that's happening? And it's just trying to remember, I guess, some of the fundamentals of.
Okay. My fallback position is stoichiometry. Write the equation so that you know what's happening in solution. Of course, the zinc sulfide has its equilibrium, and then we introduced something else. And it also has an equilibrium when it's in contact with products from the first equilibrium. In other words, pictures. You need pictures. And that's what an equation is. Okay. Let's see. Determine the ion product. Oh, okay. The ion product. What it's asking for is Q. Let's see, for the following system. Lead 2 nitrate. Yields. You know what? Lead 2 nitrate is completely soluble. So if it says 3.2 molar here, then this is going to be 3.2 molar, and this is going to be 6.4 molar. Because this is completely soluble. Right? It's not a solid. All nitrates are soluble. And then sodium chloride.
Did we memorize that somewhere?
Well,
is that one of those just commonly known things like
well,
that I am not commonly knowing?
I should have a solubility chart in here, but I don't. I'm sorry if I.
So all of nitrates are 100% soluble?
All nitrates are soluble. And all alkali metals are soluble.
Alkaline metals and
Yes.
nitrates.
So the sodium and the chlorine together, most chlorides are soluble, but all sodium salts are soluble. So this one is soluble. And it's, well, let's see. Hold it, get that out of the way. What we have here is 3.5 times 10 to the second, which is what? 350 milliliters. Of that solution. And this one is 0.020 molar. And we have 200 milliliters of that one. Okay? KSP for lead chloride. Okay. Lead 2 chloride is, this is the important part. Because when you combine these two, actually you're combining these with this one. Okay? And this tells you that lead 2 chloride is virtually insoluble. Right? If we looked it up on that chart where it has the cations and the anions, you'd find a gray box. But this is the solubility of that insoluble compound. Okay? Which means that what you got is this one combined with that one yields that. And if you talk about solubility, then you just have to flip it. That's all. Now, what's the question? Determine the ion product. Okay, so the ion product is going to be this one times this one. And since we're not talking about equilibrium, we're talking about Q. That's what ion product means. If we were talking about an equilibrium situation, we'd say solubility product. Ion product is to tell you which way the reaction is going to go. So we're talking about Q. That means this one, that one, oops, there. And I use parentheses, not brackets, because it's not equilibrium. And I didn't balance my equation, sorry. There. Right, because you got two of these, two there, there. Okay, so now what we need to do is determine what's the concentration. Now this says equilibrium, but the ion product says not equilibrium. So it's a simple matter to determine the concentration of ions. In this case, we've got 3.2 molar lead, because this one is 3.2 molar and this one's 1. And then we have 350 milliliters of it. Right? So, in order to determine the concentration of lead, we'll do it over here. So the lead concentration is going to be, how many moles of lead do you have? 3.2 molar times 350 milliliters, which is how many liters? 0.350 liters. Okay? And then we need the volume. So it's going to be this one, just like that, divided by what's the total volume, right? 350 plus 200. So that's 550 or 0.5. 0.55 liters. Should I put I'll write it down, but this way. 0.350 plus 0.2. There we go. So that's the molarity, or the concentration of the lead. 2 plus.
Oh wait, so that's not N, that's,
Well, this is N, right here. Right? Moles per liter is molarity. Okay?
so when you take moles per liter per total volume, that equals what?
Molarity, that's the ion concentration of lead before the reaction. Because lead is going to react with chloride. That's what this says right here. This says that it's going to become, it's virtually insoluble.
Ion concentration of lead before the reaction.
Okay, so this is 1.12 moles per 0.550 liters. And that's 2.036 molar. We'll bring that over here. 2036. Okay, now we have to do the chloride the same way. So the moles of chloride are 0.2 liters times 0.02 molar. Okay, there's your moles. And then it's in the same volume. So here we have 4.00 times 10 to the minus 3 moles. This is moles of lead 2. This is moles of chloride. 0.550 liters. So this concentration is 7.273 times 10 to the minus 3 mole chloride. There we go.
Wait, so then you get, so that divided by that, and then you gotta square it, right?
Right.
Over there.
Right. Mm-hmm.
Just hang on 1 second. .27 times 10 to the negative. And
What would have been a better?
so we got the
I want to change this. There we go. That's a more familiar form of the equation, where you have double replacement, end up with a precipitate and a spectator.
Oh, just combining them like that.
Right. That's the reaction that's actually going on.
Final answer, 1.08 times 10 to the negative 4.
Mm-hmm.
Is that what you got?
That's it. And then what does that tell us? Well, Q actually, we should flip that. Before we try to talk about the significance of the Q. Okay, so now that we've calculated Q for this, the ion product, we can say which direction is that reaction going to go. Well, Q is small, is what relationship to the KSP?
It's larger.
Right, it's larger than the KSP. Right, so that means the reaction is going to go that direction.
Oh, I'm sorry, I was writing, so I didn't know which way you pointed.
Hold on a second, let me think. If Q is greater than KSP, KSP says values here. No, it's going back this way. Excuse me. That means favors reactant. Right. If Q is greater than KSP, we're favoring the reaction, which means precipitation. Okay. Q is greater than KSP, you will get a precipitate. Equals. There we go. It favors precipitation.
Lead chloride and a little sharp there somewhere.
Oh, the color chart?
Yeah, it is.
Yeah, chloride.
Soluble chloride.
Oh, that'd be the first one.
Mm-hmm.
So it takes out silver, mercury 1, and lead 2 in that first step. Well, that in this case we add acid, but the chloride is the important part right here. If you know you've only got lead nitrate in solution, then you can add any form of chloride. It works.
What do you mean? When you said that, what do you mean? Say that again.
Oh, I was drawing a distinction between adding chloride as the acid or chloride as the salt. Right? If this is the only thing you've got in solution, then any chloride will work. But if you're going to use this stepwise procedure, you want to use the acid because the next step requires that H2S be an acidic solution for, let's see, for to precipitate group 2. Then you add a base, then you can precipitate group 3.
Is lead nitrate acid? Or is the salt acid?
It should be acidic. I would expect it to be acidic. Not very, but
When you talk about acids and bases without something having hydrogens involved, like what is the measure of acidity like when there's not hydrogens involved?
well, okay. What happens in solution? Well, this is that, and this is that. So, what do you have in solution, really? I mean, solution before these react, you have water, right? It's a neutral solution. So what reaction do you get with this one? Well, virtually nothing, right?
So so the lead nitrate,
But this
the
one,
acid and water's the base in that?
right, this one will produce this one, right? Which means if you're taking OH from water, right, you're removing that one, that leaves this one, makes it acidic. But this one doesn't react with water, right? It comes from a strong acid, so it's a very weak base. That means it doesn't attach itself to protons very readily. So this is virtually a spectator. The reaction of importance is this one with water, which takes the hydroxyl and leaves the proton. So that's why I said it was acidic. Well, actually, I said it was acidic because of my rule of thumb. Weak base, strong acid means acidic solution.
So much chemistry, so little time.
Sure, still recording. That's good.
Do you want to do another math one, or can I ask you a discussion one? Number 24.
Okay. 24.
I guess this is more of like a discussion, like just discussion about these things. Just eliminate. 24.
All right. Where's 24? I think I got them out of order. That's the problem. 24. Oh, wait a minute. 24 is not there. I skipped 24 in my discussions.
Yeah, 24 and 25
Skip 24 and 25.
are similar questions.
Okay. Well, now's the time.
Yeah.
Okay. So, in the qualitative analysis scheme for metal ions, how are the analytical group 1 cations separated from the other cations? Oh, just look at the chart. That's why I didn't discuss it. Analytical group 1 is separated by addition of hydrochloric acid. And it forms insoluble metal chlorides. Okay? If we just look at the chart, okay? Chart, here we go. So on the right-hand side, these are the precipitating groups.
Okay, I guess we probably follow the right chart, okay.
Right. Group 1 is the first separation that occurs by addition of hydrochloric acid, and it produces insoluble chlorides. Okay? Let's see. While we're in the neighborhood, let's do 25. How the analytical group three cations separated from the cations of analytical group 4 and 5. By this time, we've already separated out analytical group 1, making the chlorides. Then we've added H2S and separated out some sulfides. That's group 2. Now we're down to group 3. And separate group 3, we add sodium hydroxide to the acidic H2S solution. And we produce two things. Insoluble metal sulfides and insoluble metal hydroxides. So let's see, that would be D. Okay?
Wait, what? Hold on a second. But that says, I thought we had to add the sodium hydroxide.
Yeah, that's what this is right here.
Yeah, but that's not what the answer says.
This is not adding H2S.
Oh, I see what you mean. Yeah. Okay. Actually, that's worded wrong. Because if we're following the scheme, at this point, we've already got H2S in there. Right? But I'm assuming that you don't have to follow this procedure. If you only want to separate group 3s from group 4s, no, that wouldn't make any sense. Because if you do this directly by adding this plus H2S, you're going to get a conglomeration of 1s, 2s, and 3s separated from 4s and 5s. I mean, if that's what you want, fine. But the whole purpose of this scheme is to sequentially separate metals. So that needs to be worded a little differently. The key here is basic solution.
I guess what we're saying is it doesn't look like the answer lines up with.
Yeah. It doesn't line up with the schematic. You're right. So if that one shows up on the test, I'll just give it to you. I don't know.
So it just should say, D's the answer, but it just should say sodium hydroxide.
Yes. It should say the addition of sodium hydroxide
Would separate.
to acidic H2S solution.
forming insoluble metal sulfides and hydroxides. Right.
Oh, wait, so. Oh, it should be adding sodium hydroxide to the acidic solution?
Yes,
Okay, so the answer is C then, but it should say by addition of sodium hydroxide in acidic solution, forming insoluble metal sulfides.
Well,
It just doesn't say about hydroxide.
no, C is a step because H2S added to the hydrochloric acid solution will give you a separation, but it's not the one we want. So that's why D should be the correct answer, but it should be reworded. So the addition of sodium hydroxide, not H2S, sodium hydroxide to the acidic H2S solution. That's the wording. It should say
by addition of sodium hydroxide to the acidic H2S solution. Forming insoluble metal sulfides or hydroxides.
that's the way it should be worded.
Take a look.
Yeah, I need one too. I'm not going to stop this recording because every time I do, I forget to start it up again. Let's see. No message from Jimmy. Okay.
Ooh, can we go to number 26?
26. Okay.
Just moving on right along. Right there.
Why is 26 in there? Okay, there's a solubility. Oh, okay.
So, how do we?
Right, this is good. We're getting into equilibrium of complex ions.
Mm-hmm.
Yeah.
That looks complex enough to me.
Okay, this is a good one to do because it's going to inform us on our lab exercise that we're doing next week. Okay.
So we have copper hydroxide and the value, so we have a solubility product for copper hydroxide.
Uh-huh.
And then we have an equilibrium constant for copper ammonia. I don't know how to properly name it.
Yeah, tetraammonium copper 2. Let's see. I don't do these very often either. So let me get out. Go to the handout I gave you last week.
Yes, sir.
This would be a good practice for me too, if I just find it. There it is. Okay. So the ligand name is amine.
Amine?
Yeah. If it's, well, I didn't write the whole thing up there. I need to do that first. The ligand is NH3. So it's amine, A-M-M-I-N-E is the
Tetraamine?
amine, the tetraamine, and then when we put them together, we need, you do the ligand first, you name the ligand first.
Tetraamine cuprate?
No, copper 2. Tetraamine copper 2.
We don't name it like I'll just take it over.
Well, see, ammonia has no charge, right? So if the whole thing is 2+, that means it has to come from copper.
Oh.
Okay, so copper's 2+. So that's in solution, in equilibrium with and this one. And the K for this expression is 10 minus 15. Okay, so our target, let's see, I should have put the target first. Let me go over here and I'll put it. This is the target equilibrium constant equation. So we're going to have this one, which we're trying to put in solution by adding ammonia, right? Because it's solid here, and there's only a little bit of it in solution. So we're going to get it in solution by combining it with ammonia and making this complex ion. Finish writing our target. Yep.
Again, I was looking down where you're pointing. So you're saying we're trying to get copper into solution. That's the...
Right, we're trying to solubilize the copper 2 hydroxide. And we're doing it by adding ammonia. That's what this says. We're putting this into solution by adding ammonia, and it makes this complex ion. Okay, that's why this is our target equation. What we want to find out is
What's the equilibrium constant for this one? So we're going to use Hess's law. We're going to combine equations. So this one's on the right side, should be. This one is not. This one needs to be flipped because this is a product. So what we need to do is rewrite this one to give us tetramine copper 2 on the correct side of the equation. Okay. Now what does this K become?
1 over.
It becomes the inverse. Right.
Okay, so you,
Well, since this is times 1,
10 to 13.
yeah, that's it.
Okay,
Okay, you have a question?
yeah. The first thing you just did was we're trying to combine the equations.
Yes, we have 2 equations. This one gives us the reactant. This one is also a reactant. This tells us what needs to be combined. This is our target equation.
And you just flipped that so that the NH3 was now a reactant.
Yes, exactly.
Oh my goodness gracious.
So we're going to combine this one and that one, this one and that one, to give us that one, if we're lucky.
Can you pause while I write this down?
Okay.
Let this get into my brain for a second. So, point to me again why we flipped it, because of why?
Oh, because we want reactants on this side, and in this equation, that's a reactant, but it's a product here, so we need to move it over here.
Oh, okay, so in the final equation,
Because that's the target.
in the target equation,
Mm-hmm.
so you flipped it to make it a reactant.
Yes.
And when you do that, you actually have to take the inverse of that K value.
Correct.
What's the shorthand for therefore? Isn't there a little sign you make for therefore?
Uh,
Oh, yeah, I thought so. Okay, so
okay.
so
So I brought everything down. Everything from that equation down, everything from this equation down. And the copper 2 plus on both sides cancels.
And everything else is essential to the equation. But now we have the equation that matches our target. Next question is, what do you do with the K values? When you combine equations, how do you combine the Ks?
I cannot remember.
Multiply the Ks. So it'd be this one times that one gives you your K.
So did we even have to write all that other business out?
What other business?
Where you combine?
This?
Yeah.
Not necessarily.
Not necessarily.
No. You know, on a test, you're strapped for time, so as long as you know you've got things laid out correctly, then you just take the relevant
So you can
Ks.
you can combine the solubility product and a regular K value, you can multiply them
Oh, yeah.
for this purpose.
Yeah, as long as the equations combine to give you your target, then you can go to the Ks and combine those. And I get 1.6 times 10 to the
We had
minus.
that somewhere. Which chapter was that where you multiply K1 times K2 equals something? Is that on our?
It was in the equilibrium. So that would have been what, 13? Was that when we were introduced to equilibrium?
I guess it's ringing a bell. So to combine.
Yeah, 13.
You can combine two equilibrium constants that you're to find a total or a new equilibrium constant just by multiplying them.
Yes. Yeah, and I proved. You want me to do it again? Prove why you can do that?
Slow down.
Okay. Let me shut off the nitrous oxide. I'm too fast.
I just want to see if I get the right answer if I put it in my calculator. Just using this tool can be a filter for getting a question right or wrong.
Mm-hmm.
So, hold on.
Let's see, I should do it this way.
I'm going to answer 1.6 times 10 to the negative 6.
Yep.
Is that what you get?
Okay, so what does that tell us?
I have no idea.
Oh, yeah, you do. This is a very small number still.
Right.
So the equilibrium is not very far to this side. But if you compare it to this one, 10 to the minus 19 versus 10 to the minus 6, it's 13 orders of magnitude better at dissolving this than just water. So you're making a pretty big jump in solubility from that to that.
By adding ammonia.
Yeah.
Ammonia.
Ammonia. We're going to use ammonia also.
So, was that just all where you were going with that? Just the magnitude change and.
Oh, I wanted to make that point, but do you need confirmation that this times this is a valid expression of KEQ? So what would be the expression of K for this one? Would be copper 2 plus, and OH minus, right? And the valid expression for this one would be KSP. Valid expression for this one is this one. And divided by ammonia, the fourth power. Okay? So what's a valid expression for this one? It would be this one. And this one, that one doesn't count. So this one's on the bottom. There.
Why did you say that one doesn't count? Oh, because it's solid.
Because it's solid.
Sorry. Yes.
So if we take this one and multiply the whole thing through by, right, that's 1. That divided by that's 1, so we can do that. So this part that's KSP, and this part is our K. Multiply them together, you get that value. Okay.
Glad somebody else went through all that, those steps.
Did I go too far? Yeah. There we go. Now we can see the whole thing before I erase it all. I did erase this part.
It's okay.
What number was that? 20,
The happy viewers at home can press the pause button.
26. Okay. There it is, all together for my viewing audience. Okay.
How you
So-
doing back there, Sarah? How you doing back there? Back here.
So perhaps this would be a good time to go to the lab and do the same thing with what we're going to do in the lab, since it's fresh on your mind.
Yes, which day is that? That's for next week's lab.
Yeah, next week.
Do we have that already? You haven't given that handout yet. I have you.
Oh, I'm sorry. Do I even have it with me? We have to take another break for me to get it. Okay. I will pause it this time. Start it up again. Okay, so this is going to be the lab for 8. So we're going to find the formation constant. Formation constant of
Ooh, we need a flashlight for this.
Yeah, I got one right here. We're going to have to use the Tyndall effect to be able to very precisely determine the point at which precipitation happens. Because we're doing a titration.
Is it Tyndall?
Tyndall effect. I think it's 2 L's. The Tyndall effect is you have a beaker, so you can see through it. If there's nothing in it, you shine a light through it, you're not going to see unless there's smoke in there. There's nothing, you're not going to see the beam.
Right.
If there's a solution in there, and you have your flashlight, and if you have a solution in there, you're not going to see the beam either, because there's nothing to diffract the light beam. But if you have a suspension, then you've got very fine, very small particles in there. They're going to diffract the beam, and you're going to be able to see it. You'll see the beam. That's the Tyndall effect. And that's what we're going to use, because these little particles are going to be silver chloride, solid. Some people have good enough eyesight, they can see it when it forms, but mine's not good enough. Most people's not. So I'll use the Tyndall effect, then we'll know exactly when it starts, because that's the end point for our titration.
White will reflect white.
Yeah, it'll look, yeah. Okay, so if we're going to know, we're going to find out what KF is, we need to know what KF stands for. And what does KF mean? The formation constant for silver, diamine silver 1 complex ion is, if these ions in solution, we're going to have ammonia in solution. And it's going to form this complex ion. Like that. And then the KF is going to be just a simple equilibrium expression.
But we're saying F stands for formation,
Yes.
but it's still like an equilibrium.
Yes, it is an equilibrium that's happening here. Only for this part of the equation, there's no solid formed. Right? It's not a solubility product. It's an actual equilibrium between these reactants and that product.
How is the silver?
Delivered?
Yeah,
Yeah.
yeah, it looks like it's
Okay.
nitrate.
If you take a look at the method, we're going to have a silver nitrate solution. Right. Silver nitrate's going to be in the flask in the bottom. That's 4 of them. And we're going to titrate into that. We're actually going to add ammonia to each one. So we're going to form this one in solution. But unless you have some really fancy equipment, you can't measure the concentration of these easily. Right? So we're going to use a coupled reaction. to determine how much of this there is. And we're going to do that by titrating sodium chloride, potassium chloride, I think.
Yes, potassium chloride.
Potassium chloride. And in order to use potassium chloride and its reaction, chloride reaction with silver, we have to write out an equilibrium expression for those two combined equations like we did for the problem just before that, the copper hydroxide. Okay. So the other reaction that's taking place is this one. And we know the K value for this one is, I don't have it memorized. Here it is, 1.7 times 10 to the minus 10. Okay, we know that. What we don't know is this one. So what's the reaction that's happening here? It is, I thought I had it in here for me. So we're going to form that using this. So they're on the proper side now, I believe.
Do we need to write up, but we're starting with silver nitrate, so.
Yeah, the nitrate is a spectator, so it doesn't matter. Okay. So what's our target equation?
Silver plus.
So our target equation is silver here plus ammonia. Oh, wait a minute, we already got our target equation. Here's our target equation.
Right, but do we need to, where do you put in the parts with the potassium chloride and the ammonia?
Oh, okay.
Those additions.
Ammonia. We're going to include this one, the chloride, because we're titrating with it. It needs to be there. Okay.
I know that you said the nitrate is the spectator, but just for the sake of going through all of it, can we like we started, like in this other problem, how we started with the copper hydroxide, and then we had the next thing, and then we have the target equation.
Okay.
Or is that, do I
Well,
just need to not worry
Yeah,
about that?
we could do that. How did we get to this point here? So we had potassium chloride and silver nitrate. And that forms potassium nitrate plus silver chloride. Is that what you're talking about?
I guess.
But the spectators are here. So really all we're interested in is this one and that one.
So is that what we're gonna start with, is a beaker or a flask with each of those and then add ammonia to them?
We're gonna have, okay, first we're gonna have this, and then we're gonna add that to it to make this. All right, so that's our starting point in the flask. Right here.
Okay,
And then we're gonna titrate this until the solubility product is exceeded. And that combined with this will give us that. Actually, these two combined. Why didn't I write them separately?
I don't know. I mean, so the end goal is to see
Find this right here.
but also to get a precipitate?
Yes. Right.
So that's where I was getting a little
Okay.
lost. I wanted to see where are we going with this?
Right. So when the reaction, when we get a sufficient amount of chloride in there, it's going to produce this, plus actually it becomes like this. And that's what we're looking for. But we need a certain amount of this in order to produce that. Up to a certain point, adding this is not going to exceed the solubility product of silver and chlorine to give you that. So that's our end point. Okay, so KF, here we go. KF is here. And then we substitute in here the KSP, which is silver, chlorine. Okay. Okay, this is not going as smoothly as I had wanted it to.
That's probably because my brain's interrupting yours.
Well, not necessarily. Let me back up. Right now, this cannot be part of the equilibrium expression because it's a solid. So that's why we have to stick to this side over here. And this equilibrium expression, maybe this is where I need to go. It's going to be this one. Times this one divided by that one. Okay. This is the formation constant. Let's see how they compare. This right here is the KF. Oh, okay. So that's KF, right? Because this is one, so that is equal to KF. Okay?
So now that we have that, how do we fit KSP in there? Silver times chloride. Here it is. That one and that one is KSP. So if we rewrite this,
Sorry, which one and which one?
this one and that one here, those two together, that product is KSP. Let me get this out of the way. There. That one. And then on the bottom, we have the ammonia squared times the KSP. That's what these two are, KSP. So that's our final expression for KF.
KEQ, KF, so formation constant and equilibrium constant.
Right, I put this one in here first because that was this expression. But then I recognized that that divided by that is 1, so if we just make that 1, then this expression right here is the KF. So that's why this is KF also. Then we need some known values in there, and KSP is one of them. So we notice that this one times that one is KSP. Here it is right here. Then whatever's left over. So this is our final expression. This is what we're going to use to calculate KF. So the trick now is to be able to determine these values.
And that's what that example is on this page right here.
Okay, we need to set up a nice table now. And we're going to stick with this equation.
That's our target equation.
Yeah, that's the right. That's the stoichiometry that's happening in the reaction vessel. So this is the one that we're going to use for our ice table. Now, the difference is it's easier in this case, rather than using concentrations directly, to use absolute amounts and then calculate the concentrations after we determine the amounts. Okay, so we've got, in this example, we have a 5 milliliter aliquot of 0.1 molar silver nitrate is treated with 5 milliliters of 1 molar ammonia and diluted to 100 mils. So that's our starting point. So we're saying that 5 mil of silver nitrate (5 mils of 0.1 molar silver nitrate. And so we're starting with this, and then we're treating, I'm sorry?
Aliquot?
Yeah, aliquot is just a portion, a fancy word for portion. 5 milliliter portion of 0.1 molar silver nitrate. Because we're not taking the whole vessel of 0.1 molar silver nitrate, only a part of it. And then we're treating it with 5 milliliters of 1 molar ammonia. And we're diluting, the final volume is 100 milliliters. Just hold that part till later. Right now, we want to find out what does this represent. So we're starting here with 0.1 times 5 is 0.5 millimoles. Did I explain that one to you last time? Milliliters times molar is millimoles. Okay? And millimoles divided by milliliters is molar. So that's why I use millimoles, because it saves a step. And you don't have to use tiny numbers or scientific notation either. So how much of this? Well, 1 times 5 is 5 millimoles of ammonia. Okay, now there's another piece to this puzzle. The solution is titrated with 1 milliliter of 0.1 molar KCl. That's when you see that faint opalescence, that silvery white, when we shine our light through it. So here, we've got 1 milliliter of 0.1 molar. So that means 0.100 millimole of chloride.
Which came from potassium chloride?
Yes. Now, what do we got over here? 0, 0. Okay, what's the change that's going to take place? Or am I moving too fast?
We're just 1 second.
Okay. Okay, ready for the next step? Change. Okay, we've got none of this. Reaction now is going that direction. And all of this chloride is going to be used up because we formed a precipitate. So that means we're going to end up with that much there. And that means we've lost this much here. Let's see. Oh, and we have consumed, let's see, we've consumed all of the silver ions. Why? Why did we consume all the silver ions? Because we combined them with ammonia. They're all over here now. So that means we lost those. Now we have these. Oops. Get my numbers written correctly. There. Now, at this point, we've consumed all the silver ions in the formation of this product, and we've used up the chloride ions because, well, actually, we didn't really use up the chlorides because there's chloride and there's chloride, right? So it's just that ion becomes this ion over here. The reason it's over here is because that's the precise moment that you start to form a precipitate. That's why all the silver is still in here. It's not here, technically. There's a little bit of it there. But that's just so we can see when it reaches this side. But the chloride ions are still essentially chloride ions and not silver chloride. Okay, or should I just move on and maybe it'll hit you later? Okay. Okay, so how much did we lose here to make this? Well, we've got 2 ammonias here and 2 ammonias there. So that means the same amount that showed up over here, we lost over here.
That is not what you have here, though.
Oh, wait a minute. You're right. Stoichiometry is 1 to 2. So this should be -1. Right? Yeah. That's correct.
Because maybe you lost twice as much as what we.
Right. If we're going to lose that much here, it takes twice as much here. And then we make that much. And a half a millimole here means half a millimole of that means a whole millimole of that. Okay, so now the stoichiometry is correct. So what does this give us? Well, here we have 0. Here we have 4 millimoles of that left in solution. Here we have 0. Here we have 0.5. And here we have 0.1. Okay, now we have the equilibrium situation, but we can't do any calculations until we know concentration. So we need to know, if this is millimoles, we need to know how many milliliters is that dissolved in. Right. So we started off with 1 milliliter here, but we had 100 milliliters here, so this is 101 milliliters. This is 101 milliliters. This is 101. Okay. So that gives us 4 divided by that is 3.96 times 10 to the minus 3 molar. And this is 4.950 times 10 to the minus 3 molar. This is 9.01 times 4. Now we have our equilibrium values. We can plug them in the equation. Well, the one that I erased. So now the Kf, go back to the equation that I erased. So we have silver, we have diamine, silver 1 ion, we have chloride at equilibrium, squared, and KST. So
That is the
concentration for the ammonia, which goes on the bottom.
And this is at equilibrium.
And then we have our top numbers. Let's see. So
We just have to plug in the product 4.95 10 minus 3. For this one. And then the chloride is 9.901 times 10 minus 4. Yes. Then ammonia is 3.96 10 minus 3 squared. And then the KSP for silver chloride, which is 1.7 times 10 to the minus 10. Then we do that calculation.
where was the KSP?
What page is that? That's top of page 2 in bold.
Oh. You know, you can put something in bold, but it doesn't guarantee that you will find it.
Yes, that is a valuable lesson I've learned. 3.96.
It's like me leaving notes for my kids. I can leave a note on the counter, but it doesn't mean they're going to read it. And if they read it, that doesn't mean they're going to do what it says either. 2 strikes there.
Okay. 1.84, 10 to the, ooh, I got 10 to the,
Yeah, shouldn't it be 3.960 times 10 to the -2, so 10 to the -3? That's what the paper says here.
okay, hold on a second. Let me do this calculation again. The one that's wrong is this one?
Yeah, on the paper it says it should be -2.
Okay, 3.9, let's see. 4 divided by 101. Yes, that should be 2. That is correct. That means this will be 1.84 times 10 to the 7th, I think. And that's the formation constant for this. And now that we know the formation constant, it belongs to this equation right here. And if this one is competing with this one, you see that 10 to the 7th is 17 orders of magnitude higher than the solubility product for this one, which means it doesn't take much. All of it goes into solution. There's nothing left under most circumstances. Of course, we created the circumstances that balanced that solubility. Okay. Now, what did I do? Oh, the last page is just a demonstration of why this is valid. When you add ammonia solution to silver nitrate, why does this combine with that and not ammonium, NH4? Right? So that last page just shows you that it is a proof that 99.6%, if you're at 1 molar concentration of ammonia, when you put it in solution. 99.6% of it is in that form right there.
Oh, when you put it in water,
Yes.
just to show you that it's not interacting and doing something other than what you showed over here.
Right. It's not interacting with ammonium in
It
H4.
stays in H3,
Yes.
to your point.
That's why when you open a bottle of ammonia, household ammonia, hits you right in the face because it's that. And that wants to be a gas.
What's its dilution per household? I mean, it's not straight, it's like,
Oh, it's diluted.
yeah, like,
Yeah.
what is that?
You know, I don't know. Let me see.
Unimportant details of life, but
Oh,
you know,
no.
it's still, you know, just pretty.
That's handy information. Let me see. It might not give it to us in units that we
Can relate to.
readily. It's kind of like vinegar is 5% acidity. And you say, what does that mean?
Right.
Let's see. So, concentration. Let's see what it says. Measured in units of Ronak scale.
What?
Density, 26 degrees. Well, that's 30%. About 30% by weight. At 15 degrees centigrade. That's a high concentration commercial product. I would expect lesser to be marketed to the public. %.
So is that all we're gonna cover for the lab? Can we go back to the exam review?
Oh, yeah, sure. I just thought this stream of consciousness, since we covered that one problem.
Yes, I agree. It's a good thinking.
So we'll go back to the other stuff now. I don't know why Joycey likes brown so much. It breaks this really well.
It's a black.
Yeah, and it shows up. Okay. But I didn't get it from the official drawer. Bought this one myself. Okay. Number. How about those starting with 27?
That's what I was just looking at, and I wanted to see if I could, I wanted to just think about it for a minute before we do
Okay.
anything with it. Why the wording of it? Why molar solubility? Molar solubility.
That's just to distinguish it from that, the alternate. Usually what you'll see in the literature, well, in the CRC handbook, you'll see so many grams per 100 milliliters of water. That tells you solubility of any compound. But that works for soluble compounds and insoluble ones. Actually, no, this is for soluble compounds. In the CRC handbook, they say this for the soluble ones like sodium chloride, potassium chloride, nitrates, whatever.
CRC handle.
Yeah, chemical rubber company. They got a handbook that's like this thick. It's got all kinds of data in it. But they use this for soluble compounds, and we use molar solubility for the insoluble ones. The CRC handbook, if it's not a substantial value here, then they'll just say insoluble. They won't tell you what the value is. You have to look it up in a different part of the handbook for the KSP value. So molar solubility is generally identified with insoluble compounds. and they're very small values.
Okay, so you want to look at that first one?
The key to answering these questions is get the stoichiometry right. So molar solubility expression.
So first step, we're gonna write silver chloride, right?
Right.
Okay.
Silver.
AgCl.
Okay, so the KSP is going to be silver chloride. So if you know the solubility, do you know any part of this value? Well, yes. If you know the solubility of this, it's equal to that one. So if this is X, and that's X, if they're 1 to 1, you will have X here times X, which is equal to X squared. So the expression of KSP for 27 is, well, they're saying S for solubility.
So A.
So the solubility, molar solubility of this is 1, 1, 1. So that means this is S.
And it turns out we have that number here for silver chloride,
Yeah.
if we really want to know.
Uh-huh.
But the mathematical expression.
Right. Yeah. To answer the question, you don't need it.
Okay, so don't tell us the next one. And let's see if I can figure it out for number 28. Iron 3 hydroxide, so that would be Fe3, so that means it's 3 plus. Hydroxide is OH, and then we're going to need 3 of those, so it's going to be in parentheses with a little subscript 3. Right?
Mm-hmm.
Oh, see, now you're writing it out, and I said, wait.
You're supposed to keep your head down in your paper.
Okay, keep my head down. I'm not going to look that up. So iron and I dropped 3 OH. That's how it would be balanced. So to find the KSP, that would be the products Fe times OH cubed divided by Fe OH 3. So that means well, if iron is X, then that makes OH 3X. So then,
In these type of problems, it's probably a good idea to assign X or S to this side over here. And then what does it mean on this side?
okay,
Because the molar solubility is how much of that goes into solution.
how much? Okay, so you assign the iron 3 hydroxide as S in this case, because that's what they used in the answer. So on the other side, you have the ratio of 1 to 3.
Right.
So then that means on the top it's S times 3S cubed, right? You're covering that.
Yeah.
S times 3 cubed divided by, so then it actually just turns out it's 27x, S, whatever, right?
27S what? You don't have a denominator.
right? Because the denominators
They
are solid.
crossed out.
Denominators are solid, so it goes away.
Oh, I didn't think about that.
Yeah.
Solid. Oh.
Yeah.
So no denominator.
That's why they call it the solubility product,
Solid. So,
because
okay.
there's no quotient involved in solubility.
But where does the, I got the, oh, because of the other X, or S in this case, sorry.
You got this far, right? S and 3S for that one.
Uh-huh.
Okay, so then you just need to be sure and write the solubility product expression.
So
for
it's
it.
going to be S times 3S cubed.
Yes.
So that's
27
27.
S to the fourth. Because that's S cubed, and this is S to the first. It's S to the fourth. Right?
Oh, that's right.
Add the exponents.
Yeah, it's just remembering basic math here at this point.
Is that in the back of your textbook?
Probably. Yeah. It's in the appendices. Yes.
Okay, so.
Add exponents.
So 29. Silver 1 sulfide. Silver, that's 1. Sulfide is 2 minus, so that means we need 2 of these.
Sulfide. Sulfide. I'm not looking up the board yet.
Oh, okay.
Would you use SO3?
No, sulfide.
Oh, just SO.
It's just S.
Oh, it's just S.
Uh-huh.
Oh.
You okay on time?
Yeah, I think so. So silver is +1,
Okay.
but sulfur is -2.
Right.
So that means it's Ag2S.
Exactly.
And then on the other side it would be 2Ag plus S. I got it. So that makes the molar solubility be
Make this S. That's 1 to 1, so that would be, yeah. This would be 2S.
or S to the third, letter D. That's what I get.
Oh, okay. So we get 2S
2S
squared.
squared times S.
S, right. 4S to the third. Yep.
4S third.
That's right. Let's see.
Can you do 34? Ooh, I was looking at 32, because I didn't ever master that has a chapter 15 stuff in it, and I was totally bombing that text. I'm like, oh, something's buffered, oh.
Are they similar? No, they're not.
No.
You want to do 32 first?
Sarah mastered chapter 15, Stephanie did not, so
Yeah, but I didn't attest before, so
that's okay.
Okay. 32. How many moles of iron 2 hydroxide will dissolve in 1 liter of water buffered at pH 10.37?
Okay, so pH is 10.37.
What is, okay, can you just explain that to me, that sentence? Like,
What?
it says, I just have to first understand the question.
Okay. How many moles of iron 2 hydroxide will dissolve in 1 liter? That means, what's the molar concentration?
What
The
does that mean when
solubility.
you say the water's buffered at pH? Like water buffered at, so does that say that there's something else already in the water that's making it 10.37?
Yes. Yes.
So the water has something in it.
Right. pH of 7 means that hydrogen ions and hydroxyls are equal.
That's an equal neutral water. So
Right.
something's in that water already,
So if the pH is greater than 7, it's basic.
right?
That means there are hydroxyls already in the water,
Okay.
okay, in excess. So we need, this is our equation, solubility equation. And hydroxyl. Okay. And the KSP is 1.8 times 10 to the minus 15. All right. So we know that this solution is not pure water, right? Because this says that we have excess hydroxyls. What we need to do is, in order to fill out our ice table, we need to know how much of this is already there, right? So the simplest way to do that is find out what the hydroxyl concentration is. So the pK for water is equal to the pH plus pOH. This is 14. This is 10.37. And this is unknown. So the pOH is equal to, let me just put it in my calculator because I'm going to need the calculation anyway. 14 minus 10.37 is 3.63.
Yeah.
Okay.
So we have our pOH.
Right, now we need hydroxyl concentration. Right, so we got to convert this. So using the anti-log.
Wait, don't say it out loud. Just
Okay.
the hydroxyl concentration is, or the pOH equals the negative log of that concentration, right?
Yes.
Right.
Right. The negative log of the OH concentration is the pOH.
So pOH equals negative log of that concentration, and so you plugged in the number to get that. So if you say, so if you know pOH is 3.63, it equals so if you move negative log over to the other side,
Right, you're
What
saying,
happens when you divide by negative log? Do you just move it over or do you do something different?
you're saying the negative log of this one is equal to that one, right?
Right.
That far?
Yeah.
Okay. So we take the negative over here first. Negative 3.63. Okay? The base here is 10. So 10 to that power equals this. That's what logs mean.
I get that so confused. Say that again and point.
The base of the log here is 10. Right? This is common logs.
Yeah.
So the base to that power is equal to this value.
Base to that power.
To that power is equal to this one. Okay? Otherwise known as the anti-log.
So it's 10 to the negative 3.63
Mm-hmm.
is the concentration of the hydroxyls.
Right.
Oh my gosh.
Let me move this over here.
So we know now that that is the starting point of
Yes.
concentration already in when we add the iron hydroxide.
There we go.
That's the concentration of
Hydroxyl. Right. And that means that this is going to be something, and this is going to be twice something, right, because of the stoichiometry.
wait, so we put that under 2OH. Now,
Oops. So far, so good?
so when do we take into account the coefficient of 2? Or how much we added for the change? Okay.
Yeah. The change is, if we're gonna dissolve some of this, and it's gonna give us this much of that because it's 1-to-1. And then for every one of these, you get 2 of those. And then the equilibrium expression is that and that. So the question is, what's the solubility? Well, the solubility, since this is 1-to-1, the solubility is X. X is its solubility.
Because, say that again.
Because this is 1 and that's 1, then this X, soluble X, is equal to the solubility of iron 2 hydroxide. Remember when we were doing those before? S here. This has to be S because it's 1-to-1. This would be 2S. So it's S and 2S. So we want to find out what, what X is. That's that. And we need this one and this one squared, which is equal to X. And this one is 2X plus 2.344 times 10 to the minus 4 squared. Now the question is, can we ignore that X? Well, the solubility in water is this. If you already got some of this, solubility is even going to be less than that. 10 to the minus 15 is significantly smaller than 10 to the minus 4, so we can't ignore this one. So that means that this is X, and this is 2.344 times 10 to the minus 4th squared. So 1.8 times 10 to the minus 15 is equal to this value. Let's see. I already have it in here, so let me square it. And this would be, oops, 5.4, actually rounded off, 5.50 times 10 to the minus 8 x. So x is equal to this divided by that.
So why did you say we can ignore the 2x? Just, can you explain that again?
Oh, okay. Is x big enough to actually affect the total here? Okay, so we look at x, and x is the solubility, or the x value here is the solubility. So the KSP is 10 to the minus 15. So actually what we should do is say, what's the solubility in water, right? So it would be, the solubility would be x times 2x squared, which would be 4x squared, 4x to the third is 1.8 times 10 to the minus 15, and x equals 1.815. Divided by 4, and then take the cube root of that.
I still don't know how to put that in on my calculator. How do you find a cube root? I think, I don't know. I know we worked on that one day.
Yeah, that didn't work. Hold on a second. 15. Oh, that's what happened. Divided. There we go. So that's 7.66 times 10 to the minus 6. That's in pure water. So 10 to the minus 6 here is 100 times less than 10 to the minus 4. So it's not going to have any influence on that value. That's why we can say, do that. Then that leaves just this squared times that. So I get 3.27 times 10 to the minus 8 molar solubility. So, and that fits. I mean, empirically, if this is solubility in water and we add some of this to it, that's going to impede the solubility. Right? So if this is in water, and this is with our hydroxyls there, that's 10 to the minus 8, this is 10 to the minus 6, we expect that decrease. The question is, does it fit the 5% rule? So the only way to tell that is take x, put x in here, and see if it comes out to that value.
Well, so wait.
Go ahead.
We just calculated so that x, that is the concentration of iron. But now we want to know how many moles.
That is the molar concentration. Because these are in molar units, right? So that value is in molarity.
I guess it's a little confusing to me if it's asking how many moles.
Per liter,
uh,
right? That's molarity.
Right, well, it just says moles, and I think of moles as a different number, I thought. It's just confusing to me.
Until you dissolve it in 1 liter, then it becomes molarity.
Right, since we're talking about solubility, we have to, okay. Okay. It's just translating this language thing here, just a little language barrier. I'll catch up one day.
Let's hope it's soon, right? Right before the exam.
Thanks, Dr. Bly. Well, I know that took a long time to get to your question. Sarah's turn.
What was your number?
34.
34. Okay.
I know it's painful to sit here with me. Maybe some of my dumb questions help.
Sometimes you haven't explained it, but it really helps.
Well, that's, yeah.
Chromate ion is added to a saturated solution of silver chromate to reach 0.78 molar chromate ion concentration. Calculate the final concentration of silver ion at equilibrium. Okay. So we need our the balanced equation. If we're going to calculate the final concentration of silver, then we need the solubility of silver chromate. Okay. And the solubility product, KSP, is 9 times 10 to the minus 12. So the final concentration means equilibrium. So what's the equilibrium concentration of silver ion? Well, it says at equilibrium. What are we starting with? Well, this is really simpler than it looks. What we want to know is what's this one down here. So what are we starting with? Well, it says we're starting with to reach a 0.78 molar chromate. So if we're going to reach a 0.78 molar chromate, that's equilibrium, right? Actually, I don't even need the ice table. If this value is at equilibrium, then what should this be at equilibrium?
Oh.
It should be twice that, shouldn't it? Yeah.
Calculate.
Oh, wait a minute. Hold on a second. That's not right. That's not right. What's that? Scratch that. I never said that. But it is really simple. It's not that simple. Okay. So this is equation in one unknown. We know this value. We don't know this value. But we're given this value at equilibrium. Oops.
All right, so that,
So this equals this one divided by this one. This one equals the square root of this one. Just define there.
how many ions is that?
There we go. Let's see.
Well, that just seemed too easy after number 32.
Mhm.
What a letdown there. Kidding.
I'm sorry.
No. I guess the only thing there that I would have had a hiccup on is just reading through that problem and understanding that that 0.78 was the end equilibrium amount. You know, like that's where I needed to put it in the table.
Mhm.
Just knowing that that's where that was headed.
Can we do 42?
Sure. Let's see what we got here.
Okay, yeah, that looks complicated.
All right. 42.
Gosh, there's so many questions for such a short chapter. So many questions.
100 milliliter sample of solution containing 10 millimoles of calcium ion. How many millimoles of solid sodium sulfate must be added in order to cause precipitation of 99.9% of calcium as calcium sulfate?
We have to assume the volume remains constant. Otherwise, we've got a related rates problem, and that means calculus, so we don't do that.
Thank goodness.
Okay, so the controlling reaction here
is this one. This is the one we're interested in because we want to know when that starts to form. Actually, when 99.9% of that has been accomplished.
But you still write it as the reactant?
Yes, because that's the expression of KSP. (6.1 times 10 to the minus fifth), and this will be equal to that 1 to 1. Okay. All right. So we're starting with how much of this? 10 millimoles, right? Let's see, we're at 42. 10 millimoles, yes. And we want to precipitate 99.9% of that. Right? So if 99.9% is precipitated, how much is left in solution? 0.1% remains in solution, right? Okay, so 0.1 times 10, if I did that right. Oh no, 99.9%. Yeah, that's right, 1%. So you don't multiply percent times that, you multiply the fractional. So it's 0.001 times 10 millimoles equals 0.01 millimoles calcium is still in solution. Okay? Did I make too big a jump there? Okay. So now we have this expression that's equal to 6.1 times 10 to the minus fifth, and we know our calcium concentration is 0.01 divided by how many milliliters? 100 milliliters. Right. And remember, millimoles divided by milliliters is molar. So that's molar.
Okay, what, you got that?
All right, let's do that over here.
Oh, no, okay. So you got the, so we just solved for how much remains in solution divided by the total volume to get the molar concentration to plug into the KSP. I just had to say that all out loud.
Okay,
That's
let's
how my,
do a calculation down here, and then we'll fit it in up here.
but that's how my brain needed to, I just needed to hear that.
There we go. And this is sulfate equal to this one. So we just need to divide that by that, and that gives us our sulfate concentration. This will give us the sulfate concentration, which is 6.1 minus 5 and then 1, 4. So this is 6.10 times 10 to the minus 1 molar.
And then what was the question? 42. How many millimoles of solid sodium sulfate must be added?
All right. So sodium sulfate is soluble, right? And it's going to yield that which is a spectator plus this. So these are 1-to-1. So if we know how much this is, we know how much that is. Exactly, 1-to-1. So this is that molarity. If we multiply that times 100 milliliters, right, we have to assume that the volume stays the same. Then 100 times that is, let's see, 61. Yeah, 100 times 6.1. No, 100 times 0.61 is 61 millimoles of sulfate.
Okay, I missed a step somewhere.
Uh,
I'm writing down the equation for sodium.
This is just to prove that if we can find out how much this is, then we can say, if this is the answer here is 61 millimoles, then we need to add 61 millimoles of this compound because they're 1-to-1.
But so you took the concentration,
Mm-hmm. Times the volume.
okay, my brain's not quite caught up just yet.
Work backwards. We're good up here. How about here?
No, I'm good with everything. We solved for the concentration of sulfate.
Right.
And then how did we make the leap to applying that to the sodium sulfate?
Oh, all right. We found out how many millimoles of sulfate this represents because it's a 100 milliliter solution. Right. Where is it? Here.
Why do we multiply by 100 milliliters?
To get the millimoles of sulfate.
Because molarity is moles times milliliters.
Okay, that's true no matter what. The units of measure you can use here are moles per liter, or if you divide both of them through by 1,000, that one divided by 1,000 is millimoles, and that one divided by 1,000 is milliliters. Okay, so millimoles per milliliter is molarity. And that's why you can say milliliters times molarity equals millimoles. And that's what we did here. Molarity times milliliters is millimoles. But the question was, how many millimoles of sodium sulfate do we add to this solution to make 99% of that precipitate? That's why I put this one up here. If we know sulfate, then we also know sodium sulfate because it's 1-to-1. You get one sulfate for every sodium sulfate.
Okay. No? Yes? Yes, no, maybe.
I didn't do 43.
43, okay. What's the maximum concentration of iodide ions that will precipitate silver iodide, but not lead 2 iodide from a solution of blah, blah, blah. Okay.
You just spoke my language. Finally, we're on the same page.
What was it?
That tickled me.
The Peanuts cartoons? One of the cartoons where they show, I think it's maybe the teacher standing up there.
Oh, yeah.
And the kids saying,
that's
wow,
neat.
wow, wow, wow,
Yeah.
wow. That's all they hear.
That's what happens when I get on chemistry overload. That's how you start to sound. And that is no offense to you at all. Like, that's just my brain. But it's a saturation. I've reached
Okay, 43.
my carrying capacity at that point.
So we're comparing these two reactions.
Here, this one.
What, so at one point, if you add enough iodide, it's saying, like, it'll, so what are we saying? We're saying we have a solution that has lead in it and it has silver in it,
Yes.
and we're gonna add iodine until something happens.
Right.
But it's gonna be happening with silver, not the lead.
Oh, I
The
didn't finish reading.
silver precipitates, but not the lead.
That is 1.5 times 10 to the minus third molar each of those two. So let's see if I got that right. Silver 10 to the minus 16th
And lead 10 to the minus 8th. Okay. Yeah, okay. 1.4 times 10 to the minus 8. Yeah, what we want to do is precipitate this without precipitating that.
And they're both in solution.
Right. What's the maximum concentration of iodide? That's where our
You know what,
attention should
just-
focus.
Like, I get all stuck on the point, like, that we can actually calculate this. Like, my brain is like, wow, like, you can put a number on that, figure that out. Wow. Okay.
So, when it says the maximum concentration of iodide that will precipitate this but not that, we want to find out at what concentration of iodide does this just start? Maximum here, just starting here. So we're actually focused on this one.
Which one?
For this one. This one right here.
I know, right? You can't believe it. Don't
That's-
look away.
That's the one we want. So, so our starting point here is the point at which all of this has been used up. Because as you add iodide, the first one that's going to precipitate is this one because its KSP is lower. So as you add iodide, this one gets it first. Okay? So what we need to do is find out at what point is that silver used up.
Oh, there's another bit of information I haven't put up there yet. Okay, they're 1.5 times 10 to the minus third molar in each one.
Both of them. 1.5 times 10 to the minus third molar in each one of these. So we have to use up this amount. Okay. So, well, we do have to use that one after all. So the expression here is silver and iodide. So we want to use up all of this silver first. That means we plug in that value right here. And then that's what's left over. Or that's the concentration of iodide that we begin precipitating lead. Okay, so we're going to say this one and divide it by that one. Three. Okay, that's 1. And this is minus 13, right?
Can you pause right there and let me catch up?
Huh?
My brain has to understand, and then I have to write it.
Okay.
I have to,
This would be a good opportunity for a bathroom break.
concentration of silver times concentration. I had a pee too. Drank too much liquid. I'm glad you recorded that. I totally forgot.
Okay. Ready to move on?
Yeah, so that's the concentration of
Iodide at which we begin to precipitate.
how do you know that that's the point at which that begins? Like,
Oh, because all of this is used up. There's nothing left there, so this is the only thing left. It's the only game in town now. Once we've used up all this, then that's what's left. That's the point at which this starts.
So then do you plug that I in for the next I?
Right, now we're on this equation because that one's finished. So we're on this one. And yeah, this becomes the initial for that situation. And this is times 10 to the minus 13. Okay. We want, wait a minute, that's not right. Hold on a second. Oh, yes, yes. Since this is going to be the initial, when does it start precipitating? Then this will not change. That's the starting point. So we're not using any of this up. Now to say that again a different way? Okay. The question is, what's the concentration of iodide that will precipitate all of the silver iodide, but not this? So we don't want to produce any of that. That means we can't use any of this up. We just want the starting point, right? So that means the change here is 0. But how much of this do we have to add to make it happen? Because this is our starting point now. We've used all of that up. We're starting here. But we still have to add some more iodide because of this value right here. Right? So just having this little bit in there won't precipitate it. It all depends on that product right there. But this is our starting point. So we're going to have to add a little bit more X to get it going. Okay. So now we have this and this. And that goes into the expression here. And now the age-old problem. In this case, we don't want to say that X, that we can throw X out, because if we throw X out, we've got nothing to solve for, right? So we want to say that the approximation is that this is so small that it has virtually no influence on X. So that's what we're going for. Yeah, I'll put that inside. Let me put it outside first. We got rid of this because it's so small in relation to X. So that means X squared is equal to this one divided by that one. Which is a number.
Okay, 9.3. 10 to the minus 6. And then x is the square root of that number. Square root. So I get 3.1 times 10 to the minus third. And if we compare this number with that number, we're justified in saying that doesn't matter. So let's see if that answers the question. 43. Yeah. Yeah, that one's a real brain twister.
Yeah. I don't know how many more of those I can take right now. Like I just get to a point where I have to have like a gap in time for my brain to like just slow down and get it all in.
Well, let's see if there are any other problems in here that require a different thought process to let that part of your brain rest. Doesn't appear to be.
Just real quick, the formation constants, that value, KF value, explain to me again how that value, that representation relates to the KSPs. Are they related numbers? Like, how do they relate again?
Oh, okay. In those types of problems, we're using solubility to find out what the KF is.
But what does that value mean exactly?
The KF?
Yeah, that value means what?
It's just another equilibrium constant.
It's another equal.
Mm-hmm. Yep.
Where something is
We're forming a complex ion
making
with,
a solid, it's a concentration amount.
it doesn't make a solid, no.
For instance,
Just making a complex ion in solution.
right.
Okay.
We have two of these.
So let's discuss 47 then.
Oh.
That's where I'm going with this.
Okay.
Because that's where I'm sort of looking. But there's the
Good. I already started one of them.
mm-hmm.
Point 7 times 10 to the 7. And each one of them is silver.
What do we call that one? CN cyano? Yeah, cyano.
So it's dicyanosilver 1. And that should be like that. This one is
So when you have a KF, you write the complex ion as the product.
okay. Yes, that's true. Okay.
Now, let me look, what was the question? Those are the 3 complex ions of silver.
Which of the following is true? All right. 1 says this one is more stable than this one. So what do we mean by that? Well, compare the KS. Which one has the greater drive to product? 10 to the 18th or 10 to the 7th? The equilibrium constant, the KF for this, says that the greater drive is for dicyanosilver ion. So this one is false, because this one is more stable. But 10 to the 18th is a bigger number than 10 to the 7th. And everything else is equal to ammonias and 2 cyanides, so we can directly compare the KFs. Right?
So a bigger KF means that it's favoring
The product. And we can compare each one of these, actually, in terms of their KFs, because their stoichiometry is similar. 1 silver and 2 each of each one of these. So we can compare the KFs without having to worry about it.
So if we're favoring product, then we're saying the silver, however you say it, silver's
A dicyanosilver.
dicyanosilver.
Mm-hmm.
We're saying it's more stable
Yes,
because it's favored.
because that's bigger. Yeah. So that statement is false, because it says just the opposite. Two, adding, I'm just going to read NO3, HNO3, strong acid at, okay, get my terminology right. Adding strong acid to 0.01 molar silver diamino would dissociate.
Tend to dissociate.
Right. Now I'm abbreviated. Dissociate the complex. Okay. So what does that mean? That means if we can, well, here, over here. If we can do something to remove this from solution, then it will drive this reaction backwards, right? That would dissociate this complex. If we could do something to remove this one, right? I'm good so far? Okay. So what can we do to remove that one? Well, suppose we flood the system with that. This one combines with that one to make this one, and we form ammonium nitrate that removes this one from solution and dissociates the complex. So that one is true.
Does that molar amount, like that, throwing that in there, does that like even matter?
No, that's blue smoke. 3. Let's see, is that, yeah, it's still in the. Move it back some.
I guess I still don't know, like, how do you know that hydrogen is gonna combine like that? Like, how did you know that? Where did I miss, like, learning that part of this? That was a given. Like, why should I look at that and know that that's a given?
When you put this
When
in,
you put that acid in there, that it's gonna react with the ammonia.
when you put that in solution. Yes.
Yeah. I guess that's where I get lost. Like,
This automatically is like that in solution. There's some of that always there, right?
But when you
These
add
two.
the acid to that,
Well, this is not going to combine with that because it's a negative and it's a neutral. But if you add that to it, you get a positive and a negative. Then you're balanced. Well, maybe you don't know that. Now you do.
and we have video recorded
Oh, yeah.
evidence.
There's evidence. Okay, 3. Adding HNO3. To 0.010 molar.
maybe that's something from chemistry 1 that just didn't stick with me. Like, you know, that basic part right there, I don't know.
Now all we're doing is just changing this part. What happens if you put acid in that one? Does it have an influence?
No.
Right, because H and Br is a strong acid, so it's not going to associate at all. So we're looking at this one, right? In order to dissociate that, we've got to do one of 2 things. We've either got to remove this one or remove that one. HNO3 will not remove this one because silver nitrate is soluble. Right? You won't take any of that out of solution or put it in some other form. It's still just like that. So what effect does it have on bromide? Well, NO3 minus won't react with bromide because they're both anions. And HBr is a strong acid. It's completely dissociated. It has no influence either. Right? So this one, which that's the form that it will take in solution, neither one of those has an influence on either one of these. Right? So that's false. You just have to go back to the controlling reaction and see what effect each one of them has on it. And let's see. I'm trying to put this in a form that will fit on the board. All right. There's no good way to do this. To dissolve silver iodide, and this is insoluble. Add either sodium cyanide or hydrogen cyanide. Dissolve.
You said silver nitrate was soluble?
Yes, right. All nitrates are soluble.
You said that like probably a few times today, at least.
I can say it again. Okay. This statement, fewer moles of sodium cyanide are required. All right. So what's the controlling reaction? Well, we've got here, this one. Which form of cyanide really is the question. Will produce the desired effect. So if we add cyanide, just simply cyanide, doesn't matter where it comes from, then we will dissolve more of this. Right? And that will produce this one. Except we need two of these. And then we'll have the iodine here. Like that. Okay. So that's the reaction we're talking about. And we're just concerned with, does the form of cyanide make a difference? Okay. This is not information that's given in the problem, so that's a bad problem in that respect.
Well, that's why I'm like, well, how?
Yeah. Okay. Here's the point. Sodium cyanide in solution forms sodium and cyanide completely soluble. In fact, it all goes that way. Okay? So however much you put into this, you get all of that. How about HCN?
But how do you know that? Like, how did you know that? Where did that information come from? How do you
Yes.
know? Yeah. When did we learn that? That's where I get lost. I'm like, when did I learn, or what was I supposed to learn that?
Oh yeah, all sodium salts are soluble.
But 100% arrow going that way.
Right.
when did I learn that and how did I miss that and like not retain it? Like that's where I get
Okay.
That's where I get really frustrated and where
Okay.
I get stuck on problems. So I'm like, I don't know. Like, how am I supposed to know that?
Yeah. In part, that was my fault because I gave you that chart of solubility, and the rules are down below, and I emphasized the chart, but the rules down below say,
From Chem1, that chart, the solubility.
yes,
Oh,
yeah. all sodium
the
salts
gray
are soluble.
boxes.
Yeah, that one.
Okay.
But hydrocyanic, let's see. Yeah, hydrocyanic acid is a weak acid. So it produces this and this, but less of this. And that produces more for the same amount that you add. Same molar amount that you add, you'll get more of this and less of that.
Why?
This is the weak acid. Hydrocyanic acid is weak, very weak. Probably, it would be better, this problem would be better if that information were put in the problem. Right? Sodium cyanide is completely soluble. Hydrocyanic acid has a solubility and a KEQ of some value less than 1, a lot less than 1. So if you're given those values, then that would be easier to deduce these two and find that this is, oh, excuse me, that's true. Fewer moles of sodium cyanide are required because all of it goes into solution. Okay? So 2 and 4.
Okay, so what we're saying is that if you wanted to dissolve the silver dicyanide, whatever that is, dicyanide, silver.
If you want to, right, if you want to convert silver iodide into the dicyano silver complex ion, the more effective way, the fewer moles required, would be sodium cyanide.
Just because it's more like it, because it just splits up.
It's completely soluble, yes.
Completely soluble, so it just wants to do that. It
Right,
wants
that
to
gives
break
you more of
apart
these.
into- Okay.
Right, for less sodium cyanide, you get the same effect as more hydrocyanic acid.
Just I wouldn't have been able to connect all those dots. I just don't, because I wouldn't have, like, my memory bank wasn't holding on to, well, first of all, sodium cyanide is going to completely dissociate in one direction. So, and just to know, like, that reasoning, that whole logic there, like, was lost on me
I understand.
from just not, I guess, retaining and pulling forward enough information from past.
Yeah, and
That's where I get stuck, is how there's so much, it's voluminous, the amount of information to keep
yeah,
forward.
that's why they call chemistry the central science. It steals from everybody.
Steals my soul. Little soul sucker. So number 4 is true.
Yes.
Okay,
So
that's the bottom line there.
Two,
I don't know how many more of these problems I can go through right now.
well, we only got 20 minutes left. Maybe this is a good time to break. Rather than fret over the rest of them.
I'm getting to fret point, reaching my saturation.
Yeah, I understand.
53 questions out of this little bitty bit to chew on and stress over.
Let's see. There are actually 8 pages. $56 points. 21 bonus. So I tried not to stress you out in this chapter because it was such a bear with concepts. And application, that's the thing. The concepts are not that difficult. It's applying them to problem solution. That's where we get sticky.
Yeah.
Are we calling it a day?
I think so, don't you?
I do, me personally, how about you, Sarah? You okay with break?
Yeah. Like, and this is how I have to study at home, because I have to do it in chunks, and then I needed time. And I just have to have a rest period, and then I can come back and try again.
Oh, yeah. Small bites.
Thank you, Dr. Wine.
See you next week.
Ready or not, here we go.
Let's see, we can stop this.